Hello once again and welcome back to this video lecture in ABE164. And in this video we'll be discussing our next topic, which is about capacitors and inductors. Besides resistors, capacitors are the most common electrical components, and they can be found extensively in electronics systems, in computers, power systems. So that's the reason why I have included it here for our discussions. Okay, so recall that we have already said that a capacitor is a passive element, and it's an element that is designed to store energy. So somehow that when there's a voltage source, that somehow it stores that energy in a form of electric field. And later on, when we need that energy, then we can have that energy from this. Supplied by these capacitors. Okay, so just like in the applications of electric motors, wherein the starting effort sometimes is hard. So sometimes of motors have these capacitor types. So somehow it can help that start. Help that in its starting requirements. Also, for the flashing of the cameras. So if we need that energy, where do we get that? We get that from capacitors. Okay, so the parameter for capacitors is what we call capacitance. Okay, so it's right here, capacitance, and its measured, or its units, is in farads. We have these equations right here that it relates the charge and the voltage. So somehow the information that we can get is that if we have more voltage, then somehow we can get more charge. And if we have a capacitance, or the capacity to store that energy, or to store the charge, then if we have a larger capacitance, then we can also have larger magnitude of charges. Okay, so think about capacitor as something like a storage tank. So the more capacitance that you have, or the larger your tank is, the greater charge that you can store. And also the voltage, or something like the pressure, then if there's a lot more pressure, then you can store more charges. Okay, so that's our working equation. So just keep this in mind for now, because later on we'll be using this in our computations. So the charge Q, which is measured in coulombs, is equal to C times the voltage. Right? The C is the capacitance, C in farads, and V is the voltage in volts. Okay, another equations that we'll encounter also is in terms of the construction. So typically the construction of a capacitor is that there is these two plates. We have two plates. We have these blue plates, top and bottom, and we have these dielectric materials, or insulator, that somehow it doesn't allow to pass the let's say the electrons or the protons. So one type of charge is in this plate. So let's say we have a negative charge in this plates, and then later on in this plates, or in this bottom plates, we have a positive charge. So it somehow separates the charges, because it doesn't allow to pass it through this dielectric material, right? So just like resistors, that we have also equations for that, regarding the resistance, taking into account the resistivity of materials and the length and the area. So just these capacitors we have here, the capacitance is also equal to the permittivity of the electric materials, the surface area of each plate, and the distance between. So we can get a lot of information from here. Anything that's the numerator, that's directly proportional, and anything in the denominator is inversely proportional. Okay, but we're not gonna do much computations for that. Now let's move on to how it works. Right? So how it works. So we said that capacitors are devices that stores energy in electric field. So how does it do that? And so supposedly, or suppose that here's our capacitor. So at this moment it has no charge, so the plates are neutral. And then if we connect this to a battery or to a voltage source, then somehow there's going to be a flow of current, and the flow of current will will not allow to pass through the negative charge or the other charges. So somehow the negative charges will stay on this plate. Let's say on this orange plate, right? And there's gonna be an accumulations because the negative are stuck in here. So the positive charges will be accumulating in this at this side. Okay, so as this battery supplies the voltage and the charges, right? So of course at time zero, the storage or uh, or the charge inside the capacitor is zero until it reaches its capacity. So just like storing a water in a tank. So let's say here's our tank, and then at first we fill it with water, so until it gets to its full capacity. So just like here, so it gets to its full capacity. So one charge is separated, negative, and the other one is positive. And because of this plus and minus, then somehow there's going to be an electric field. So I'm not sure whether it's negative to plus or plus to minus. But anyway, there's going to be an electric field. And we can also see that there's going to be voltage. I mean plus here and minus, so somehow there's going to be a voltage difference. So somehow if we need that energy or we need that pressure later on, then we can use it for later purpose. Okay, so that's the basic idea. And then also in terms of the storage tank, so we said that first the tank is empty, and then we filled it with water. So at time zero it's empty, and then up to some time that it reaches its full capacity. So that full capacity, let's say this is subjected to atmospheric pressure, and somehow that height is equivalent to the pressure. Right, so that pressure is something like the push of water along the pipes. Right, so if you have more water in here, more height or more charges, then you have more energy. Okay, so that's the basic principles of this capacitors. Okay, so if we connect it into a circuit, so let's say we have a voltage source, we have a switch, and we have a capacitor and a light bulb right here. So if we connect it, if there is no capacitors, so assuming there is no capacitor, so if there is no capacitor, then if we turn on the switch, then the current will actually just flow through the wires, and then this bulb will light up. Okay, and when we turn this off, then of course when we turn this off, then the bulb will turn off, right? So instantaneously it will turn off. But if we have this capacitor connected, then if we turn this on, then some portion of the charge will be received by these capacitors, and somehow it will start to accumulate right here. So it will start to accumulate until it reaches its capacity. And what will happen is that when we turn this off, when we turn this switch off, then of course this will not be connected anymore. So there is no more power coming from the source. But because they are, I mean, the capacitor and the light bulb is still connected, then somehow this stored energy will be released, and to further continue the operation of this light bulb. But of course, it will only last for some time, because eventually this will die down. Eventually, this will be emptied, and therefore, if it's empty, then it cannot turn on the light anymore. But the point here is that at some instant of time, if you need that energy, then we can use this capacitor. Okay, so next, the VI relationship, voltage current relationship. The current is proportional to the rate of at which the voltage across the capacitor varies with time, or mathematically it can express with this: I is equal to C times the rate of change of voltage with respect to time. So something like the Ohm's law, but it's not the Ohm's law because it's not resistance, but it is a relationship between the voltage and the current relationship. And take note that this voltage is a rate of change of voltage, so instantaneous rate of change of voltage. So if you want to know the voltage or the I, then we can take since it involves, it's an equation that involves derivatives, then somehow we can get into differential equations or solutions for differential equations. Okay, so at any time t, we can determine the amount of voltage or the the I. Okay, next is the power in the capacitors. So the instantaneous power delivered to the capacitor is still the same, P is equal to VI, except that since I is equal to this, so that equations becomes something like extended. Okay, and the energy stored is the area under the curve. So we have this graph right here. We have a graph of time versus the energy. So that's going to be the power, right? And the area under the curve is actually since it's P is equal to VI, so our voltage is this, right? So it's an increasing curve, and then we have this decreasing curve for the, I think this should be I, right? And if we multiply P times VI, so let's say P times this, so we get this point, and P times this, you get this point. So that's why we have this power curve over here, and that's the energy stored in the capacitor. Okay, so of course it will just reach its maximum, so depending upon the capacity of that capacitor, so that's why there's going to be some maximum value. Okay, and the area under the curve can actually be solved using this equation. So using calculus, and if you derive it, derive the solutions, then we can get this 1/2 times C times V squared. Right, so that's the energy, and then since V is we know that Q is equal to CV, right? And if you substitute that, so somehow we can get another equation for this energy with respect to charge and the capacitance, whereas this one is energy with respect to capacitance and the voltage. Okay, so next one is we'll talk about capacitors in series and parallel. So just like resistors, we can also place capacitors in series or in parallel, and thereby increasing or decreasing the level of capacitance. So right here we have a series connection, and right here we have a parallel connection. Now in terms of voltage and current, it's actually the same. It's almost not almost, it's actually exactly the same as the series and parallel connection for resistors. So you see that the voltage, the total voltage is just equal to the voltage drops across each resistors, but here across each capacitors. But the I, or the amperes, the current, it's the same current. If it's in series, it's the same, and if it is in parallel, then the voltage is the same. So right here we have this voltage, let's say 12 volts. We can have 12 volts, you can have 12 volts, 12 volts, which is typical for parallel connections. Okay, so next one is capacitance. Now the capacitance is actually the opposite. If we compare this, to a resistor, because in a resistor this reciprocal behavior or characteristics is in parallel connections, but for capacitors this reciprocal behavior appears in a series connection. Okay, and for parallel, it's just simply the sum of the capacitance. Okay, and another property that's included here is the charge, because sometimes we are also interested in finding the energy or the charge stored in that capacitor, so we will need this equation. So this one is the same as this as the current. So for series connection, the total charge is just equal to the total charge is just equal to the charge that enters here, the charge that's across or that's stored here, and the charge that's across here, C3. Okay, so I think that's all, and now we'll do a sample problem. Okay, so first sample problem is taken from one of our reference texts. So for the circuit shown, it says find the total capacitance, determine the charge on each plate, and find the voltage across each capacitor. We have the capacitors in series, and the value of capacitors are given, so we can actually use this equation to find the total and somehow work our way to find the charge on each plate and to find the voltage across each capacitor. Okay, so to do that, then first is, okay, so let's write our solution. So solution, first one is, since all the capacitance are given, then solve for total capacitance or equivalent capacitance, total. Okay, and recall that this is in series, so because it's in series, then that's 1 all over CT is equal to 1 all over C1 plus 1 all over C2 plus 1 all over C3. Okay, so if we substitute the values, C1 is 250 and 10, so 1 all over 200. Take note of the unit. This is microfarads. So if it's microfarads, that's times 10 to the negative 6, right? Plus 1 all over what is that? 50. So again, 50 times 10 to the negative 6 plus 1 all over 10. So 10 times 10 to the negative 6. Okay, so if we do the calculation, what we get is 125,000, and this will be in farads because we already evaluate the micro into times 10 to the negative 6. Right, so again, because it's a reciprocal, then we need to take the 1 divided by 125,000 farads to get the total capacitance. So CT is equal to 8 times 10 to the negative 6 farads, so which is just equal to times 10 to the negative 6. This is micro. So 8 microfarads. Okay, next step is maybe we'll write it here. So next step is we're already done with letter A. Then next, determine the charge on each plate. So the charge on each plate is, so since this is a series connection, then recall that QT is equal to Q1 is equal to Q2 is equal to Q3. And also our equation that Q is equal to CV. So recall this. So if we are going to use the total capacitance, this will be total voltage, right? So if this is total capacitance, total voltage, this will be total Q, total charge, right? So therefore QT is equal to CT times VT, which is just equal to, what is CT? That's 8 microfarads. So 8 microfarads, right, times the voltage. The voltage is 60, so 60 volts. And if you do the computations, that's gonna be 480, 480. The units of this is coulombs. So this is micro, so should be 480 micro coulombs. So don't confuse this C for this C, because this one is capacitance, right? This one is capacitance, whereas this one is a unit of charge, which is coulombs. Okay, so next one is, okay, the voltage across each capacitor. Okay, so find the voltage. Okay, so the voltage across each capacitor is, okay, so voltage across each capacitor is, again, from the equation Q is equal to CV. So if this is C1, then it should be, if this is C1, this one should be Q1, this one should be the voltage at that, or at that capacitor number 1. Okay, so therefore we have this value, we have this value, because the Q is the same all throughout this series connected capacitors. The Q is 480, so 480, 480, 480. So therefore the capacitance is also given, and therefore V1 is equal to Q1 all over C1. Well, let's just write QT, it's the same. Then V2 is equal to Q2 all over C2, and V3 is equal to Q3 all over C3. Okay, so let's substitute all the values. We have here, this is 480 microcoulombs. This is also 480 microcoulombs, 480 microcoulombs. Then the capacitance is 250 and 10. So 250 and 10, and the unit is microfarads, microfarads, microfarads. And if we do the computation, what we get here is 2.4 volts, 9.6 volts, and 4.8 volts. Okay, so to do a recap on what we did, we are asked to find the total capacitance, and we are asked to find the charge on each plate, and also find the voltage across each resistors. And what we did was to simply apply these relationships or equations here, and our main equations of this capacitance is the ratio of the charge per unit charge, charge per unit voltage. Right, so I can write this Q as all over V. So the amount of charge per unit voltage, and we just apply that, and then first we solve for the equivalent capacitance or the total capacitance, and what we get is 8 microfarads. And then after that we solve for the total charge, because the total charge, if we know the total charge, that's going to be the same for the charge in this capacitor C1, C2, and C3. So it's the same. And what else? And for the voltage across each capacitor, because we have Q, we know Q and the capacitance are given, then we can solve for V1, V2, and V3. Okay, so I guess that's all for this video. In the next In the next lecture, we'll do a computations for parallel connection and a combined series and parallel connections for capacitors. So see you in the next video.